All right. So after our math review and discussion of vectors, I think we're now ready to really start into physics. First big topic we're going to discuss is called kinematics. And basically what kinematics is the study of the motion of objects. And what we're going to do is we're going to develop a series of equations, mainly two big equations, but sometimes three or four, which relate important concepts, important characteristics of motion for objects, and see how they relate using math. Now, the first big characteristic we need to know has the variable x, and it's the distance. Sometimes you'll also see it as displacement or position. Basically, it tells you where something is, and in general, when we discuss the distance traveled, we mean the difference between two positions. You were here, you've now gone to here, you've traveled a certain distance. The unit of measure that we're going to use in physics and most science fields is, in the metric system, little m for meters. Okay, so we're not using the imperial system like we do here in America with feet and inches and things. Engineers use that here. But for the most part, in science and in almost the whole world, the metric system is used. And it's used because it's beneficial mathematically. It makes math easier. It makes converting units easier because you're using factors of 10. So for instance, you can have centimeters, which is 1/100th of a meter. So you could break up a meter into 100 bits, and each one is a centimeter, or a millimeter, that's 1/1000th. You have bytes, that's how much data in a computer. Kilobytes is 1,000 bytes, megabytes is 1,000,000 bytes, gigabytes is 1,000,000,000, and so forth. So with the metric system, the units are easier, and thus the numbers come out a little easier when you use a metric system. Now, in the real world, there's a lot of good things about the imperial system, which is what America uses. Yes, it makes converting and stuff like that difficult in science, but there's actual true economic reasons why we use things like 12 inches in a foot and stuff like that, or a dozen in a gross and things like this. It turns out having things in factors of 12 is a lot better than factors of 10 because you can divide into 12 more easily than you can divide into 10. But because human beings were born with 10 fingers and 10 toes, we use a decimal system, which is factors of 10. Anyway, so the first big variable we need to know is x, and that's the distance traveled. The next one is t, which is time. Because, of course, when you're talking about motion, in general, time comes into play. How long did it take to get somewhere? Things like this. The unit is the second, little s. And then with these two characteristics, we could come up with more complicated and more interesting variables. For instance, if you say that you traveled a distance of 2 meters and it took you 1 second to do it, then there's some new information you just gained, and that is how fast you must have been going for that to be true. And so the next one is called v, velocity. And the velocity is a measure of how far you went and how long did it take to go that far. And so the unit is meters per second. So of course we're used to in our everyday life things like miles per hour, how fast we're driving in our car and such. But in physics we're going to use meters per second. And now one thing you can notice is, and this is true in all of physics, if you know the units of something, then you can automatically tell what the equation is to find it. So let's say we don't know what the equation for velocity is. If I wanted to figure out what the equation was, then I'd just look at its units. And the way I'd do it is like this. I'd say, okay, velocity equals something, and I want to figure out what that something is. What do I know? I know the units on the left is meters per second. And there's a rule about units. There's actually two rules. The first main rule is that if you have an equation, then the left side of the equation must have exactly the same units as the right side. The next rule is, in an equation, if you're adding terms together, then each term must have the same units. Those are two big rules about units. For us right now, we only care about the first one. Looking at this equation, velocity equals something. I know the left side has to have units of meters per second, so I know the right side better have meters per second as well. So how can I get units of meters per second given what I already know? Well, I know the only thing with units of meters is distance. So I know it must be something like a distance on top. And the only thing with seconds is time, so there must be a time on the bottom. And indeed, the real equation is what's called the change in distance divided by the change in time. So how far did you go? Divide that by how long did it take to get there. That's the velocity. Now, just so you know, change, this little triangle symbol, delta, means change. And it's defined as change in position, for instance, or the distance is the final position minus the initial position. And the same for the time. Final time minus initial time. So whenever you see something like the change in x or the change in y, that means final y minus initial y. And so we have our first big equation. Velocity is the change in distance per time. How far did you go? Divided by how long did it take to go that far? And you have your velocity. All right, well, that's pretty good. We've got one more big characteristic we need to know, and that's called the acceleration A. What this is, well, what if you're traveling in your car, you notice you're not always traveling at exactly the same speed. Sometimes you slow down for a red light. Sometimes you may speed up to get around a car. You're changing your velocity all the time. So we need some way of representing this change, and it turns out acceleration is the way we represent it. The units for acceleration are meters per second squared. Now, I've already told you how we define acceleration. It's the change in your velocity. So the equation acceleration is the change in velocity over time. So the more you change your speed, the bigger your velocity is going to be. Now we could always check the units just to make sure this equation is correct. Acceleration, meters over second squared. Let's look at the right. Units of velocity is meters per second. Time on the bottom is seconds. And if you remember how to work with fractions on top of fractions, this is the same as meters over seconds times seconds, which is meters per second squared. So indeed, they check out. So here's our equations. One for velocity, one for acceleration. Now, what we're going to be doing is kind of working our way into the subject, starting with easy stuff and eventually getting to the more complicated stuff. And the best way to do that is, let's start with motion in only one dimension. And what that means is 1D kinematics. One dimension just refers to the fact that in the real world, we can move in any direction we want. We can move left to right, up and down, back and forth. That's 3 dimensions. But the more dimensions we worry about, the more complicated our equations are going to look. So let's look simply first, understand how it works, and that way when we go to higher dimensions, we're not going to be confused by the letters and stuff. So one-dimensional kinematics basically means if this is the line, and let's say this is the 0 point, then an object can start, let's say, here and eventually get to here. Let's say this is the 1 and this is the 7 meter mark. So this little ball on this line can only move left and right. It can't move up and down or back and forth. It's stuck to one dimension. That's what we mean by one-dimensional kinematics. So what equations will we need to be able to solve problems? I'm going to give them up to you straight up. That way you have them up front, and then we'll see how to be able to use these things. So the big equations. These are the equations of kinematics. The first is acceleration is change in velocity over time. We already had that. Okay. Now, the next two are a little bit more complicated than we saw before. Here we have an equation for velocity is change in position over time. However, that equation is only true if you're not accelerating. Because notice the equation doesn't say anything about a in it. So this equation only works for very special circumstances when you're going at constant velocity. What we need are equations that always work, whether we're accelerating or not. Now, the way we're going to get to it is we're going to say, okay, let's start with the equation we had. Velocity is change in x over t. And for whatever reason, I'm going to rewrite the equation solving for x. So to do it, of course, I multiply by t, but I have to do it on the other side too. And so what happens, the t's cancel out, and I get x equals v times t. And this makes sense. If I said, you're traveling 5 meters per second, so your v is 5 meters per second, and you travel for a time of 10 seconds, and I wanted to know how far do you go. I guarantee you, if I asked you the question, you'd be able to tell me, well, you went 50 meters. But now what you have to do is ask yourself, how did you do that? How do you know? Because I bet you're not thinking about answering the question in terms of an equation, you're just doing it intuitively. But what I'm going to show you is this is an actual equation. This equation right here, x is v times t, is what you're doing to solve that type of problem. You're taking how fast am I going, 5 meters in every second. If I go for 10 seconds, then every second I'm getting another 5. 5 times 10 is 50. So this is a nice equation. But like I said, this equation does not account for acceleration. Now, if we were doing calculus, then there's a way to show from calculus what I'm about to write. But let's not worry about where it comes from. Just accept that this is true. The real equation we're going to use is x equals v naught t. So far it looks just like the other equation. X is v times t. Only now I'm being very specific that the v we're talking about is initial velocity. Because if you're allowed to accelerate, your velocity can change. And so if you need to write down the velocity, which velocity do you use? I'm being specific here and telling you use the initial velocity. But now I'm going to add a term that accounts for the acceleration. And that term is 1/2 at squared. So this is our first big kinematics equation. I don't really count the acceleration one. It is an equation, and you will use it. But in terms of real kinematics equation, this one is your first one. This allows you to solve a bunch of different problems. What does it allow you to calculate? Well, you can either calculate the position, how far something went, a distance. You can calculate the initial velocity of an object. How long did it take to do what it did? Or what was its acceleration? Those are all things you can solve from this equation. So, this is another important point to understand. When you're given an equation, don't just think the equation is for whatever's on the left side. For instance, acceleration is change in velocity over time. You don't only use that equation to solve for acceleration. You can also use that equation to solve for time. Or you can use the equation to solve for velocity. It just depends what thing you're looking for. This equation allows you to solve for any of the variables, not just one of them. All right, good. So that's our second equation. What's our last equation we're going to need? Well, if you notice, both of these equations involve time. So if I gave you a problem where an object's moving in some way, but I don't tell you the time involved, then you're stuck. You don't have information about time, so you can't plug time into this equation to get a number. So we need some other equation that relates these variables together, but does not include time in it. And that equation is this. Vf squared, so the final velocity of an object squared, is v naught squared, initial velocity of the object squared, plus 2 times the acceleration times the distance traveled. And now we have our three big kinematics equations. And what you're going to find is every single problem I give you in kinematics can be solved using one or more of these equations. You won't need any other equation, just these. And you can solve every one. The key, as you're going to find out, is to figure out which equation should I use. Of course, that's the problem. That's what makes the difference between someone who just picks up a physics formula sheet and can read off equations and someone who can actually solve a problem. You can't just rely on knowing what the equations are. You have to be able to listen to the problem, understand the system, and then choose from your list of equations which one will work. And that's what we're going to spend a lot of time on, of course. So let's take an example. What are some physics problems involving kinematics that we may run into? All right, let's think. First example. All right, how about this? A car starts from rest and speeds up to a final velocity of 20 meters per second if it took 4 seconds to attain this velocity. What is the car's acceleration? So this is a typical physics problem, kinematics. I'm going to walk you through my thought process. How do I think about these problems? How do I solve the problems? The first thing I do when I read the problem, I try to write down everything I know. So let's read it and see if we can pick out pieces of information that are useful. A car starts from rest and speeds up. Okay, I already know one important thing. The car starts from rest. That tells me the initial velocity of the car must have been 0. It starts from rest, so its initial velocity is 0. It speeds up, so I know there's some acceleration involved, to a final velocity of 20. Okay, so final velocity is 20 meters per second. If it took 4 seconds to do this, okay, so the time it took to change the velocity was 4 seconds. What is the car's acceleration? I'm looking for acceleration. All right, so now I've read the question, understood the system, found all the pieces of information that are given in the problem. What is it I'm looking for? And now I can start looking at the equations to figure out how to solve the problem. So let me write down the equations and see which one we may want to use. X equals v naught t plus 1/2 at squared. Vf squared is v naught squared plus 2ax. And acceleration is change in velocity over time. Now, when I was a student in college, I unfortunately was forced to memorize all my equations. We were never given a formula sheet or anything during class. So I made it a habit, because I have a very poor memory, I made it a habit that I would write down every equation for each problem. That way I'd never forget them. If I kept having to write them down, I'd always remember them. It helped me memorize. So here they are, all three written down. And now all I have to do is figure out which one should I use. And the way I do it is quite easy. I just start looking at them. I say, okay, what about this first equation? X is v naught t plus 1/2 at squared. Can I use the equation? In order to answer that, I say, okay, what am I looking for? I'm looking for A. Does the equation have an A in it? Yes, the A is right there. Good. All right. The only other thing we need to know is if A is the thing I'm looking for, then every other variable in that problem I must know the number for. If I don't know the number for one of these variables, then there's 2 variables in my problem I don't know. And I know from algebra, you cannot solve a single equation with 2 unknowns. So the only way I'm going to be able to use this equation is if I know all the variables except for the one I'm looking for. So let's see. Do I know t, time? Yep, I have time. Do I know v naught? Do I know the initial velocity? Yep, I have v naught. Do I know x, the distance? Do I know how far the car traveled? No, I'm not given that in a problem. All right, so can't use that equation. He's gone. Let's look at the next one. Does this have A in it? Yep, there's the A right there. Do I know all the pieces of information? VF, I have VF. V naught, I have V naught. A, I'm looking for. X, again, I don't have X. I don't know the distance, so can't use him. All right, well, I got one more to go, so I better have all of this information, because if I don't, then I'm really stuck. So let's see. Does it have A? Yes, it has A. Do I know everything else? Okay, it has a T. I know T. What's this delta V again? Let's rewrite it. Delta V meant VF minus V naught. So do I have VF? Yes, I have VF. Do I have V naught? Yes, I have V naught. So here we go. I can use this equation because A is the thing I'm looking for, and all the other variables I know the numbers for. So now I just use it. Acceleration is VF minus V naught over T. VF, 20, minus V naught, 0. over the time, 4 seconds. And this is 5 meters per second squared. And there we go. Solved my kinematics problem. This is the method I use for every single physics problem I solve. I try to write down everything I'm given in my problem, and I write down the things I'm looking for. I just put a question mark next to them. Next, either you have your formula sheet or you write down the formulas and you just start going through the formulas. Which one of these formulas can I use to solve this particular problem? So start on the first one. Does it have the thing you're looking for in it? If it does, do you know all the other pieces of information? If you do, then you can use that equation. If you don't have all the pieces of information, then you have to move to the next one. And you just keep asking yourself these questions until you find an equation that meets all the criteria. Once you found it, then you just plug the numbers in, do the algebra, have whatever is necessary, and you solve the problem. So let's try another example. All right, example 2. What should we do? How about, okay, a car traveling at 30 meters per second slows, to a stop with an acceleration of, let's say, 5 meters per second squared. How far does the car travel by the time it stops? All right. So here we have another kinematics problem. So again, let me first list what I know, and then we can move from there. A car traveling at 30 meters per second slows. Okay, so here's a car. It starts with a certain speed, and it's now changing its speed. So the initial velocity is 30. It slows to a stop. Okay, that tells me something. If it slows to a stop, that means the final velocity of this car must be 0 because it stopped. So the final velocity is 0. And it does this with an acceleration of 5. Okay, so I know the acceleration, but we have to be very careful. I'm being told we're slowing down, so we're going from some speed down to 0. If we're slowing, then that means the acceleration is negative acceleration. This is one thing you have to get used to in terms of terminology. When we talk in everyday life, acceleration means speed up, deceleration means we slow down. But in physics, there's no such thing as deceleration. They're all accelerations. But you can have a positive acceleration, which means you speed up, or you can have a negative acceleration, which means you slow down. So, here I'm told we're slowing to a stop with an acceleration of 5. That means our acceleration is minus 5 meters per second squared. So be very careful about that. All right. Next, how far does the car travel by the time it stops? Okay. So I'm looking for how far it goes. That's in distance. And that's what I have. I know the initial velocity, I know the final velocity, I know the acceleration, and I'm looking for a distance. Okay, so again, Let me write out my equations so I don't forget them. X is v naught t plus 1/2 at squared. Vf squared is v naught squared plus 2ax. And acceleration is final minus initial velocity over time. All right, so same process as before. Let's start asking the questions. I'm looking for a distance. Does the first equation have distance in it? Yes, there's the x right there. All right, do I know everything else? Initial velocity, I've got it. T, I don't have time. All right, so I can't use the first one because I don't know t. All right, let's move to the second equation. Again, I'm looking for distance, and there's distance right there. Do I know everything else? VF, I have VF, that's 0. V naught, I have V naught, that's 30. Acceleration, I have A, it's -5. So I could use the second equation. So there we go. Let's use it. Second equation says VF squared is V naught squared plus 2 times A times X. Now I could plug my numbers in. VF, that's 0, equals initial velocity, V naught squared, that's 30 squared, plus 2 times the acceleration, -5, times x, the distance I'm looking for. All right, so there's our equation. X, this is the thing I'm looking for. So now it's just a matter of doing the algebra to solve for x. So let's do it. I'm looking for x, so bring all the other stuff to the other side. So 30 squared, that's 900. Bring 900 to the other side, that becomes -900, equals 2 times -5 times x. All right, then 2 times -5, that's -10. So divide this side by -10, divide that side by -10. And you get x equals 90. And there we go. So there's another example. Kinematics problem. You're given some pieces of information about the motion of this car. Write down what you're given. Write down what you're looking for. Look at the equations you have available to work with. And then start asking the questions. What is it I'm looking for? Do I have this piece of information? And so on, until you find an equation that can be used. Once you have it, then stick your numbers in and do whatever algebra is necessary to get to your final answer. So this is what we're going to be doing. We're going to start with one dimensions. And then after we get fairly good with one-dimensional kinematics, we're going to move on to two-dimensional kinematics, where things can move both up and down and left and right. One thing I do want to make special mention of now is, let's say we do a problem that the object's moving up and down. So you throw a rock into the air, or you drop a rock off a cliff. Something very important to know is that the acceleration due to gravity is a very special number. It's called little g, and it's equal to 9.8 meters per second squared. Okay, so if we're going to be working on a problem, which we'll see a lot of problems like this, where you have a rock, let's say here's a cliff, there's a rock up here, you drop the rock, then I could say, how long does it take for the rock to hit the ground? Well, there's one thing you have to be very aware of, even though it may not be stated in the problem. And that is, gravity affects the rock. The reason the rock is going to hit the ground is because gravity is pulling down on it. So even though I may not say in the problem, the acceleration due to gravity is blah, 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 you have to recognize that gravity is involved, and because gravity is involved, there is an acceleration. That acceleration is downwards. It's a downwards acceleration, and its value is 9.8. So downwards, as you're going to see, If we take up to be the positive direction, downwards the negative direction, so a lot of times we'll say the acceleration due to gravity is negative 9.8. This is just something you have to memorize. In other problems like this one, where we're given the acceleration of the car is 5, you don't know what the acceleration is. You have to be given. But for gravity on Earth, you have to memorize the acceleration when gravity is involved in the y direction is downwards 9.8. Okay? So very important. Get used to that. Memorize it. Don't ever forget 9.8. And a lot of times it's going to be negative 9.8 because it points downwards. But I will be posting soon another video with some more example problems. I'll also post a bunch of practice problems up on Canvas so you can start practicing these kinematics equations. But at the end of the day, these are your big equations. So get your formula sheet from Canvas, have it prepared to start using so you don't have to memorize these things. But these equations you're going to be seeing a lot of for the next week or two. So get used to them, understand what they are, be comfortable manipulating them algebraically, and you should be fairly good with these kinematics problems. All right, till next time.